All right, awesome. So welcome back to 10th recitation. We only have this one and then two more. Yeah, and then we're done with the course. So whoever didn't watch the video, the recording, it's okay. This is, I will go over at the end, I go over the subtopics that we've gone through and what we haven't gone through. So we haven't gone through type dynamic programming yet and greedy algorithms. Both of those we'll have two recitations and two lectures on dynamic programming, one on greedy, and also one lecture on greedy. So really we finished most of the topics. We can go through it afterwards. But my point here is that we finished most of the material and you can already start solving tests. Greedy hasn't been on any test from what I know. They added it in last year and it wasn't on the test last year. Dynamic programming was in the test last year, but in most tests, there is no dynamic programming. So what you can do is you can ask ChatGPT, you can send the file to ChatGPT, say, here's the test. Does it have dynamic programming on it? If he says no, you can solve the whole test. So you can do simulations if you want. You can start solving questions by question. I also recommend, I'm just going to finish my sentence about, I recommend if you have Gemini Premium, which you can get if you're a student for a year, you just send them your app on the Bar-Ilan app, you get free Gemini, and it can go from Google Drive. You can open Gemini right there in Google Drive. You can ask it, give me 5 questions on divide and conquer. And it'll give you questions on that topic. So you can practice per topic, which is what I like to do because I like seeing the topic a bunch and then understanding what kind of problems there are instead of just jumping around. So that's what I recommend. Artem, you had a question?
Yeah, do you know when the exam is?
The exam, yeah, it's on the Lambda. It's like a week after school ends.
Yeah, I think it's on the 8th, so like the beginning of February.
Something like that, yeah. It's like a week after the school ends. It's on like a Thursday or Friday. Um,
Friday.
Friday? Great.
Friday.
I have to come too. All right, so before we get into dynamic programming, this lecture, this recitation is on dynamic programming. We have a lot to cover. I just want to do a little recap on Unit 5 that you guys finished in the lecture, right? You finished in the lecture yesterday. So here's, I took this from the lecture. It's a summary of all the different implementations of Union Find, right? You had the abstract idea and you had a bunch of implementations getting better from the naive to the best one, right? You can go through them afterwards, but what's important here is that you have these upside down trees. And also when you do union between two groups, you take the smaller one and add it to the bigger one. And because of that, and also whenever you find something, you shorten the path. Whenever you like number 7, you have 7 point to the root. And also 2, you have it point to the root. You shorten paths. So if you have those two tricks that save time in the future, the time is of making the whole union set is O of 1. And then finding within the union set, finding you just go to our array here and you look it up and it costs O of log n if our tree is really, really, really long. Union is O of 1 time. Taking 2, we just add the smaller to the bigger one, and that's it. So you also see we also have the size of each upside down tree. You went through this in depth in the lecture. But what's important is that this part is that if you take the amortized analysis of this implementation, you get find a union in log star n, which might cause trauma for some of you. But you don't have to, we're not going to go over the proof. It's that's what we're going to do in the recitation. We're just going to go over this usage of union find. So because we've learned nothing else in this course that has amortized time of O of log star n. So if you see something of amortized log O of log star n, you know it's union find. Okay, so there's actually a question that we're about to do from last year, which actually failed a lot of people. When in actuality, you see here, there's O of log star n amortized. So you know you have to use union. And then also you have this, which is O of 1 in an average case. O of 1 average
It's using
should throw you of what should it remind you of?
I mean, I was going to say amortization, like simple amortization, not like worst case.
Well, it's not amortization, it's
Yeah.
average case.
But damage is not worse, right? So it's
Amortized is, I think it's not the same. You can't use them interchangeably, but this is the same as expected. It's not, it's almost the same. If something is an expected of O of 1, it's also average over 1. Okay, not the other way around. Just remember, if they want an average, you can use expected. Okay, so what is expected? It reminds you of hashing. That's the thing that we learned that uses expected time is hashing. So you already know, just from the times that they give you, you already know, without even reading the question, you already know basically what the solution is going to entail. Some sort of hash table and some sort of union find. Okay, so now let's read the problem. They give us abstract idea of some sort of data structure, and we have to implement it. So our data structure supports these following operations. Init is to initialize the whole data structure with m different soccer groups, 8 different soccer teams that are numbered from 1 to m. So you have m different soccer teams, and we have to initialize it in O of m time. Okay, so that's the first action, the first operation. Second one is new player ID and I. So it gets an ID of the player, and I is the number of the team. So it adds our player, which has a unique ID, to the team I. Very simple. Each team means players. And then they want this in O of 1 average. Okay, now by this operation takes 2 teams. It's as if the team I buys the team J. So basically all the players in team J move to team I. And team J closes. Can't accept any more players and it can't buy any other groups. Okay? So yeah, that's what it says here. Any attempt to buy a group that already was bought causes an error. Okay? And then same group, you get 2 IDs of players, and it checks it. Are they in the same group? All right, so it returns true if they're in the same group, false if they're not in the same group. And this is also O of log star n amortized. Okay? This says the amount of memory you have to achieve. You have to achieve it in O of n plus n memory. Okay, where n is the amount of players and m is the amount of teams. Just an example, just to kind of really hone it in. This is a runtime example. You initialize with 5 different groups. You have this new player with this ID on the second team. You have a new player with this ID on the third team. And then we run the operation, same group on the 2 players. This one's in team 2. This one's in team 3. So they're not. So it'll return false because we're not on the same team. We now buy 2, 3. So all the players of team 3 are moved to team 2. So then when we run same group, it'll output true because we moved in the second team bought third team. So now they're both on the second team. Okay, so you obviously have to, yeah, it's like what the heck.
Wow.
But you already have clues from the runtime. You know you need union find, you know you need hash table. Okay?
yeah. I mean,
But it's a big
Okay, it's a big question. So we have to also they realize it's a big question and they say you have to explain the data structure to describe it. You have to describe the implementations of every single operation in pseudocode. You don't have to write any written explanation. All it is required is pseudocode. So you have to describe, it literally takes like 2 sentences once you have the answer, the data structure, and then write pseudocode for each one of the operations, and then explain why the runtime is the required runtime. So you don't need to write a whole long thing. The answer itself is quite short, actually. Okay?
yeah.
All right. Now trying to think about it. Yeah.
On the exam, can we use proven things from the lectures?
Yes.
Like, can I just say ring hashing? Let's use cuckoo hashing.
Exactly. Exactly.
You're saying that's the time.
Yes.
That's cuckoo hashing. That's all I need.
That's all you need. Exactly. As long as we learned it in the lecture, you can say we used it.
And yeah, as long as it doesn't say let's prove it. But yeah.
Exactly. Even if it says prove it, you can say if you use something that we used in the lecture and proved in the lecture, you can totally
I mean,
to
what
say
what
correct.
what I was saying is that last year on this thing, there was some question that was prove it, and people answered as proven in the lecture set. Say you can find takes long to start.
And they got points off.
They got 35 points, like got the full thing after, even if it says prove it.
Exactly. You're allowed to, if we showed something in the lecture, you can assume it's proof. You can assume it's correct. If you have to change it, then you have to reprove it.
Sure.
Okay?
But everything, like, almost everything would be proved.
Yeah, exactly. Yeah. And even if we didn't prove it, we can see like you can still use it as if it's proof. If we showed it in the lecture and the recitation. But if you change it a little bit, if you take like in the question, you had to take in one of the homeworks, you had to take like quick sort and change it a little bit. Take merge sort and change it a little bit to count the number of swaps. You have to prove it all over again. Then you changed it. All right, so now let's try and think of how to do this. These are our 4 operations. And these are the times that we need. Right, so first we have our teams, right? We have the teams and we have the players. These two are separated. They're not really connected. All that matters is players. Each player has a team. But the teams and the players, we can separate them. So which one do you think we'll use union find? Which one do you think we'll use a hash table? Exactly. Why? Because we have this operation by, which is basically a different word for merge, right? It's basically take this group, merge it into that group. Right? So we'll just use here, we'll use union find. And that's how we'll merge groups. And in players, we'll have a hash table which maps what to what?
Players to
A player to the team, right? So this
yeah, I think it's new player goes to
player.
goes to a team automatically. Yeah, okay.
Yeah. So this would cost O1, right? Okay. Now there's a little bit more details that we have to talk about. One of them is for the player to team. Once that team is bought, should this update?
No. Well, the team is null in the inverse tree, right? So
Exactly. So we have the inverse tree. Look, it's where we just drew it like this way. You have an inverse tree, right? So let's say our player is sent to the first team that he's assigned to, right? It's his original team. Now, his original team was bought by a different team. Let's say this is his original team, and he was bought by this team. Therefore, we can just use this team number and use union find to find the team that now owns that team.
yeah, I think
That's why we don't actually need to update this. We can just keep it as is. Okay?
I think the key insight here is that each node in the union found isn't a player, it's a team. So
Exactly.
that
Exactly.
skip that.
So once you're able to do that separation, the rest of it falls into place. It's just little minor details. So let's just see the answer. We have a hash table, like Artem said, a coup hash table, because we want O of 1 worst case and O of 1 average for inserting, right? Because we also know that it's a dynamic, right? The case that we're in is dynamic. You can always enter new players. It's dynamic, it's not static. So you couldn't use the FKS that we learned in the recitation, you'd have to use cuckoo hashing. So therefore we have to use cuckoo hashing that maps, like we said, verbally, and then union find, which has the groups. And then in addition, also, we're gonna have an array that basically says whether or not that group is bought. Because if a group is bought and you try and add a player to it, or you try and buy it again, you have to throw an error. So we have to keep an indicator if a group is bought. So then you also need another array of bought, yeah. Which is just an array of true or false. Size of n also. Okay, so this is just a pseudocode. It's really short. This is the whole answer, right? First, initialize is we have a new hash table. That's it, empty hash table with cuckoo hash table. And then we have to initialize the groups, right? For each I from 1 to m, we have to make set with that same group. So we're basically making a group with just that team, and we're setting the whole bot array to false because nothing's bottom in the game. So it's just initialize. Okay. Next is new player, right? We want to add a new player. If the team that we entered is bot, return an error, right? Throw an error.
Sorry. The bot,
This one?
Yeah.
Yeah.
Where's the array?
It's just a bit on the.
Oh, like where do we initialize it? Also, the make step we didn't really initialize. You're right. You should put it here. You're right. You should initialize it here. You should have bot.
I mean,
Yeah.
the reason bot is there is to make it simpler because it's a union find. You can't do a union between sets. Like they don't want you to do unions between subsets.
Exactly. But you also have to throw an error if that happens. And also, if a player gets sent to a team that's bot, that you can't check with union find.
And we also have to have the big, the column
Okay.
is n plus m. So
Exactly.
we have to do another array.
Exactly. So we're allowed to do another word, right? Because 2n is still O of n. Exactly. So you see, we have a hash table which grows to the biggest it can grow is O of n, right? There's the amount of players. And then our union find is O of n. Okay. And now our new player is basically we're adding a new player to the hash table, right? If the I is bot, then it's an error. If that team is bot, you can't add it. Throw an error. If it's not bot, then we insert it to the hash table. ID maps to I. That player's ID maps to the ith team.
Yeah.
Okay. Now by I and j, if bot j, return an error. Technically, also if I is bot, return an error. But if you go back to the requirements of the question, it says only if j is bot, return an error.
Yeah.
So technically, proper if you would have done also if I, you would have gone full points. You wouldn't. No one would take off points. But in the question, you only need j, and then we turn j to true because j is now a bot, and we do union between j and I.
Wow.
It's that simple.
That's it.
It's that simple. And then same group is basically you want to go to the hash table, right? You want to find the first group that he was in, right? So you have the two IDs. So you want to first get ID, the first group it was in, and then within the union find, you find the group that owns that group, right? The team that owns that team. So first you find each player's first team, and then from that first team you find the team that now owns it, and you compare if those two are the same. Okay.
This feels like there's a lot of things that are implicit here.
Yeah, a lot of things because we use like make set without having to go to the implementation. But I went over the test.
Not only that, it's like makes it you don't like initialize the union set, you have to initialize it.
You're saying like initialize the set here, yeah.
Thanks.
Okay, so I forgot like to initialize up here
Would we get full points?
you would get full points.
Sure.
We get full points? Yes.
It's right. Union.
Yep.
So
That's right. That's the
because
if you go back, you
big,
have these three things, and also for fine, you just write fine.
yes.
It's huge, yeah. It's a big operation. There's a lot of things, but because we learned it in the lecture, you can just use it. Yeah, it's funny.
You get fine.
Again,
If you don't specify what find does, like should we like write it somewhere that find is actually
If you want, but it's understood. It'll be understood. Like in this case, if you have to write two sentences about these two sentences about the data structure, right? It asks for two sentences describing the data structure. You write these two sentences, and when you say fine, then it'll be understood there.
Is there
The union
a good name for the union find algorithm?
A good name?
Like Google hashing, because there's many like sets.
Oh, just you say union find the implementation that we used in the lecture, or you can say the upside down tree with path compressing.
Yeah, just this show.
If you want to define it, but if not, it's understood.
Okay.
oh,
The O of M.
just to look out the ratings. So,
Oh, and the question, the original question.
of one,
Oops.
like this, just next to the.
So no, you'd have to write a little bit of an explanation about this. And also that's what it asked for in the question, right? It asked for
Why and why?
describing it in the end, and also describe like explain why all those terms. All right, so that was just the union find. There is a part two. We don't have time to get to it right now, but it's basically just adding another function, another operation of history. It's also very straightforward. The answer is up here. You can look at it in your free time, but we have to get to our next topic. It's dynamic programming, fun stuff. All right, so who can tell me if you're in the lecture what dynamic programming is, what that idea is?
Yeah.
It's skipping all the past iterations of your algorithm. Saved somewhere.
Exactly. It starts with first. I'll go even farther back. That it starts with a divide and conquer algorithm, a recursive algorithm, in other words.
Yeah.
It starts with one of those algorithms, and then, like Artem said, at each recursive call, if we already computed that same answer, we don't want to call it again. We want to save runtime using memory. So you saw in the lecture, and we also went over it in the divide and conquer recitation. We saw Fibonacci number, right? It's just the simplest and most straightforward problem to solve with dynamic programming. So first off, if we were to draw the recursion tree, it would look something like this. F of
Okay.
n, exactly that. F of n minus 1, f of n minus 2, f of n minus 3, f of n minus 4, because each one also, does anyone need me to remind what the definition of Fibonacci is? It's just the sum of the previous two. So you can see here that we do many computations for f of n minus 3, and so on, it gets more and more and more. If we just save this, the next time we get to it, we can just stop there.
Yeah.
So we don't have to so we compute everything once. So then how do we solve this? We initialize an array, right? We start from the bottom. Each one is the sum of the previous two. You just sum the previous two, and that takes O of n instead of what's the runtime of doing it recursively?
What?
What's the runtime of calculating Fibonacci number recursively?
2 to the power of n.
2 to the power of n.
To the power of
2 to the power of n. Oh, of 2 to the power of n.
Divided by the Gauss ratio or something, yeah.
Yeah. But it's big O of 2 to the power of n. Anyways. Okay, so first, this is another paradigm. Okay, we learned first paradigm was divide and conquer. This is the second paradigm, dynamic programming, which is built off of divide and conquer. It's a way of making divide and conquer algorithms faster using memory. And then the third paradigm we're going to learn is greedy algorithms. So that's basically what I said here. But a paradigm is the way we approach solving a certain algorithmic problem. Okay, it's our approach to solving it. Okay, so for which kind of problems are we going to use dynamic programming? Because this is very important. So first off, just problems that we can use recursive, because right, the whole point of dynamic programming is taking the recursive answer and making it more efficient using memory. So first you have to be able to solve it with a recursive solution, with the divide and conquer solution. And the second is what? Why in Fibonacci can we save runtime?
Smaller problems.
If we have the same subproblem that we're calculating multiple times, right? F of n minus 3
And
happens 3 times, right? And so on and so forth. So we have a bunch of redundant computations that we can save if we use memory. Now, what's a good example of a divide and conquer that you can't use dynamic programming to solve? Merge sort, which we went over. You can't use dynamic programming to reduce the runtime of merge sort. Number one, because it would ruin the lower bound of comparison algorithms. But 2, because each time you recursively call the algorithm, it's on a different subarray, and there won't be any 2 of the same subarrays. Like each one will be different. So therefore, there will never be a recursive call that was already called somewhere else. So merge sort is a good example of something that you can't do dynamic programming. And this is the second criteria, that you have computations that happen multiple times. Okay? All right. So instead of calculating it every time of that same subproblem, we're just going to solve it one time and save it somewhere. Okay, so there's two different ways of solving it. One is top down, which is called memoization. And the second is bottom up. So this one really, this is bottom up, because we're solving it from the smallest number, from the basically the bottom of the tree, up to the top. Exactly. We're starting from the base case, we're moving up to the number that we're trying to calculate. Top down would be, let's start really recursively. And every time we calculate a certain number, let's save it in an array. And if we get to a certain f of n minus 3, we've already calculated it. We always check in our memory if we've already calculated it. So it would be top down, because you just do the recursive calls. And the second you get to a certain number that you've already calculated, you don't have to call it recursively anymore. You can just use it. And that would be top down. It's a little less intuitive.
We didn't speak about it.
We didn't speak about it. Yeah, in the lecture, we didn't speak about it. In this course, we're mostly going to be doing this. I don't think there's any example of this that we do in this course. But just so you know that it exists, that there's a different way of solving all these problems. Okay, so SADAP is initials of SADAP Pulot, which is basically just saying this is the order of operations that we want to solve our dynamic programming problems. So first we always start with a naive algorithm. Just try all the possible options, check if they're valid, if they're a correct solution, and then check if they're optimal. Because most of these things we're going to check if something is optimal. So that's the naive solution. Just try all the options, try all of them. Then we need a recursive algorithm, which includes these 4 things. We'll get into that. And we need these 4 things, which is basically the formula itself. We'll define them soon. The base case, right? And you need to explain the idea of it. It's a little less important. Like there's some of these that are more important, some of them are more important. And the proof of the correctness of your recursive formula. And then the dynamic programming correctness will just derive directly from the recursive formula. Okay, so those are the 4 things you need to do. And then the dynamic programming solution. So you have the naive, recursive, and then dynamic programming. Dynamic programming is how you take the recursive and then turn it, use memory to basically make it more efficient. And we'll see 2 examples today of like a full. We'll go through all of these, and we'll solve some really cool problems that wouldn't be that simple otherwise, and will take a lot of runtime. So this is the knapsack problem with full integers. Okay, so first, a little story. We have a robber who wants to rob a certain store. He wants to make the maximum amount of profit, right? But he can't carry everything, right? In an ideal world, could Superman take everything and make all of that profit, right? So he knows exactly how much each object weighs and how much each object will make him profit. And we want to maximize his profit. And now we're bound by B, which is the most amount he can take. Okay. So you've for sure seen this in Intro to Computer Science. It's on like a lot of tests, but we're going to solve it again. This time a little more formally. We're going to get into the runtime, which you didn't do in Intro. So a robber is he's not lazy, and his only desire is to maximize his profit. Okay, so he wants to maximize the profit. So we need to help him choose which items to choose that will maximize his profit. But remember, he can't take more than B. Okay, so defining it in other ways, in a little bit more computer sciencey ways, we have an input and an output, right? This is a great like story time, but we always want to talk in inputs and outputs. So our input is we have an array of values, how much profit he's going to make, and an array of weights, how much each item costs. So if I want to know the value of the second item, that's V2, and the weight of the second item is W2. Okay? And then we're also given the maximum he can carry in his knapsack, which is B. Okay? Now the output is the value of the largest group, the largest subgroup of our elements, of our items, such that for every single, for the sum of all the weights within our that he chose to take is smaller or equal to B. Therefore, we didn't pass the weight parameter, and also the sum of the values of all the items we took is maximized, is the largest. Okay, so any ideas on how to do this? Well, also, it's very important. All the numbers are whole integers. We don't have some sort of 1.5. We have whole numbers only. Also, the values, also the weights, and also nothing's really zero. No value is zero, because if the value is zero, we can just ignore it. And also weights, you can assume will not be zero.
So I can outside the weight that then hide from me,
What do you mean?
the weight of something that is bigger than me. I don't want to.
Exactly, exactly. That's the other thing you also want to ignore is if we have some sort of item that its weight is larger than B, you definitely can't take it no matter what. So also you can assume that it's less than B. Now, if our robber had no limit on B, what would be the optimal solution? Take everything, exactly. So we can also assume that you can't take everything. Because if the sum of all this is less than B, then you can just take everything and there's no problem. Okay? All right, any ideas? What? Okay. One last thing is you're not allowed to take part of like you can't cut the thing
Yeah.
off.
So
Okay.
think you can
Or the naive.
there.
Naive.
I mean, naive.
What's the naive solution? Remember, I'm just gonna go through this. We have the naive solution, and then we go to the recursive solution. Okay, so first the naive. How do we do it?
You just start with one pointer and go increment the amount until you max out kind of thing.
So you're thinking though, like in code. I want you to think more in theoretical computer science.
Can I say?
Like you can just do, hey Sammy, you say.
It's you just take all the possible iterations of I.
Wait, you're cutting out. I can't hear you so well.
Can you hear me better now?
Yeah.
Okay, so you take all the possible subsets, all the permutations.
No, can't hear you again.
Okay, never mind.
Never mind. Okay. All right. So what were you saying, Thomas? What's your idea? Now think about it in theoretical.
So
You don't have to deal with pointers. Nothing. Just give me a solution. What's the naive solution? The naive solution we said was always trying all the different possibilities and then only taking the ones that are first valid, that they are less than that the weight is less than P, and then taking the max out of all of those. So our naive solution would just be we're going to go through all of the different options of taking items. And how many of them are there? There's 2 to the power of n. Because each item we can either take it or not take it. So it's 2 to the power of n. Exactly. And then for every single subset, we check if it's valid, if that subgroup is valid, that it doesn't surpass our limitation of B. And then we're going to take the maximum out of all those. Right? It's very straightforward. The naive is usually pretty straightforward. It's just do all the options, take the best one.
Yeah, take the first one, the best one. How we do it?
You keep you can keep an array and like you're thinking about code. How do we do it, right?
I mean, isn't this like the same as the recursive solution?
Almost,
code.
almost.
You can use bitwise equations. Like every number is zeros and ones, and you can imagine that the set, if it's one, you take that, and if it's not, you don't take it. And if you go through 0 to 2 power of n, you then go through all the possible subsets.
And then also, how do you know, like, how do you keep the maximum? How do you find the maximum? You just keep
You keep
a
track of
maximum variable, which has a maximum size and a maximum array.
So
Yeah, so really it's of n times 2 to the power of n.
Yeah.
Yeah, you're right. So because you're right, so the runtime here is really correct. Here they're right, it's at least 2 to the power of n, but you're right, the actual runtime is n times 2 to the power of n.
is it the problem where we have limited capacity and we need to take the maximum?
Yeah.
Yeah, exactly. Knapsack, the knapsack problem. It's something very I'm sure you know already. Okay. So now let's try and think of a better solution.
Yes.
I'm just gonna propose something here and let me know what you think. We want to get the maximum amount of profit, right? So why don't we take just always the item that gives us the most profit? Let's take that over and over again.
That wouldn't work in the end
Why wouldn't that work?
because of the weight. You can take.
I just take until I don't pass the weight.
Yeah, but
Why doesn't that work?
maybe some items with lower value have lower weight and you can get more in. So you.
Maybe, but maybe not. Maybe you might.
Um. We can.
Yeah, the little weight has like a smaller value, but you can take more of it.
Yeah.
That's what Thomas is saying. Exactly. Exactly. So if you have one which gives you the highest value, which is 51, let's say you have 100. Let's say you have b equals 100. So even though your top value gives you 51 and it costs you, also the weight is 51. You could have two elements that are each 50, and you can get 100. Okay? Now, I'm going to propose a little bit of a different solution. Instead of, because I don't, if there's a. Mhm.
Offering to do this question with numbers.
Do I offer to do this with numbers? What do you
To
mean?
try to.
Oh, yeah. Do I suggest trying it a little bit? Yes.
No, try the solution to put number for the question. The number like.
Like to try a concrete example? Like to try a concrete example to try and like understand it.
Yeah.
Yeah. It's very, yeah. It's important to do. Just understand. Yeah. It helps me understand. Some people can just see it and understand. I need to write a little example. Okay. So now remember in our previous example we had 51 and then we had two 50s, right? So we took this one, not this one. Now I want to propose a different solution. What if I took, instead of always the largest number, what if I always took the instead of the largest, like the one that gets me the most money, I get the one with the ratio, right? If I have like let's say a grand piano, which technically gets me the most amount of money, but it's huge, right? Grand piano is huge. And I have a diamond ring, which gets me a little bit less money, but it's very easy to take. So I'll take the diamond ring before I take the grand piano. What's the problem with that solution?
Yeah, the same.
Even
Same idea.
If you found the best ratios, you still can maybe not be filling it up as much as possible.
Exactly. So like for this one, if we have 51, or even if we give it 75 value, but it costs us 51 weight. Right? So we take this one because it gives us the best ratio, right? These are just 1. These both are 1. And this one gives us higher than 1. So we take this one, which is just another bad example. Now, this is a very good direction, an approach to solve it. We'll see in greedy algorithms. This is also a greedy algorithm. Always take the one with the highest ratio. That's a greedy algorithm where each time you make a greedy decision, which is basically a greedy decision is just making a decision based on the information you have right now. So this would be a greedy algorithm. It doesn't work for here, but we'll see a different example where this same exact idea does work. Okay, we'll see it in the future. Now, how do we actually solve it? Think about the next step. We did the naive one, And now the recursive.
The recursive is the solution.
Yes.
What?
The recursive is the solution. I mean, it's the same idea, no?
What's it as this or as the naive?
That's the naive.
It's not the same exact idea.
I mean, you
Maybe
go.
if people.
Because you want to define a recursive function that equals something. You probably did this in the lecture, right?
Yeah.
You take a function, you take a certain input, and it gives you a certain output,
Yeah,
and then you call it on the first step.
yeah. You either for each recursive function you both take the next item and not take the next item until the last item, except if you exceed the weight.
Okay, but let's define it a little bit more formally. You guys are right. So this is first what I just explained verbally, and then now we have our recursive one, right? For a recursive solution, first off, before we get to technical things, because you have the right idea, but we're going to define it a little bit more formally. Our recursive solution is divide and conquer, right? We want to take our big problem and we want to divide it into a little bit smaller problem, right? In divide and conquer, what we do is we say, I'll solve this huge problem. But if you give me a little bit of a smaller problem, the answer to that, I can solve my bigger problem now. And then recursively, you call it on smaller and smaller arrays until you get to some sort of base case, and then it returns back up. Because if I have an answer, I can calculate that, take that smaller answer, calculate something a little bit bigger, and so on and so forth, right? So for our recursive solution, we want to basically turn our big problem into smaller problems. But then if we had those answers, we could solve the bigger problem. What is it? So how do we make the problem smaller, right? If we have like divide and conquer and merge sort, you have an array, you make it a little bit smaller. It's very straightforward. But here you have
Or
elements.
take the.
Exactly, you take the head. Exactly, or you cut it down. Exactly. Here it's a little bit harder, right? Here it's a little bit. How do you make it a little bit smaller, right? We have three different ways of making it smaller. We can take less items. We can always say if I know the answer for having less items, I can solve it for that one new item. We can say the size of the bag. If I had a smaller bag, and now I'm giving a little bit of a bigger bag, I can now solve the problem. Like or even the value of the items, right? If I had the solution for a certain up until a certain amount of value, I can solve it for this new value. There's different ways of turning this bigger problem into smaller problems. Mosquito for the recording afterwards. I'm not crazy. I promise.
I can agree that it's a mosquito. I don't know if they can score, but
No, no, I missed it.
yeah.
Okay. All right. So what do you guys think? Which one should we take? The first one? Like the most intuitive. Yeah, take up until like just
Like
everyone's add one item and see if you add it, if you don't add it.
Another one.
Exactly. That's really the solution. But we're actually in this one, it's a little bit more complex. We're not only going to do one, we're going to do two on two different axes. Okay. So we're going to define it. J is the items we're allowed to take up until J. So item, let's say if J equals 3, we're allowed to take items 1, 2, and 3. Okay? And we're also going to take B, which is B is the weight that we're allowed to take. Okay, so our function is going to get two parameters, not just one. And it's going to return according to those two parameters. Okay, so we're really going across two axes. We're ignoring the third one. But we're going across those two first axes.
Are you adding the amount of items as a restriction or as an optimization? I don't understand.
As a restriction to our formula.
Okay.
It's not, we're not getting up to optimization yet. Okay, so we're making our problem smaller, making it into a smaller subproblem by constricting the amount of items and also the weight that we're allowed to take. So if J is 0, what does this equal? No matter what B is.
0.
It's 0, because if I'm not allowed to take any of the items, it'll be 0. And if B is 0, what's the
0.
0? So those are our two base cases, right? Okay. So this is basically what I said verbally. So FJB is going to be the largest value that the robber can take from the house with the j first items, and using weight at most b. Okay, so that's first we define our recursive function. Okay, that's also the first step. If I would go back to the order of operations in the recursive functions, one of them is just defining your recursive function and explaining what this means, right? What is j? What is b? What does fjb return? So that's our first thing. J is just the amount of items we're allowed to take. B is the weight we're allowed to take, and then it outputs the maximum amount that we can steal with those items and that
Good one, sorry.
value. Yeah.
Every item you can take an unlimited amount of times.
No. Don't take each item once.
Okay.
Okay. You can either take it or don't take it, right? If you're stealing a diamond ring, can't steal the same diamond ring again. And in computer programming, you're right. Sometimes you want to solve the problem where you can take things over again. Okay. So like we said, base cases first are first of j equals 0 equals 0, right? And also there's another base case that actually you said before is if the weight is greater than b, then we're allowed to take, then we can't take that item. So if we can't take that item, it won't be equal 0. It'll be equal to fj minus 1, like without not including our item that's too big, and the same b. Okay? Does that make sense? We're basically saying if you can't steal this item because it'll be too big, right? Then don't steal that item, and then the value of this will be just the value of the one before it, because we can't steal that item. It's too big. It could be we can steal it for a different recursive call of the function if b is bigger. So if
Sorry,
it's bigger, we can maybe take it in the future.
sorry. J goes down, doesn't go up. No.
J goes down. J is based off of the previous ones. Yeah.
No, yeah. I mean, first we start with fj and b, and then if we take an item, we go to fj minus 1 b. So this should be j plus 1.
This
Yeah. No, fjb equals
is j minus 1. The element, if we could take all the elements up until the jth item, and the same amount,
okay.
right? Because we can't take the element, the jth element, so it would be just equal to the one before. Otherwise, if j is not equal to 0, so we can take a certain amount of elements, and also we can take the element because if we add it, if the weight of it is not greater than b, that means we can take it, right? If the weight is smaller than b, then we have two options. What are the two options?
Take or we don't take.
Exactly. We take or we don't take, right? That's basically the naive one. We take or we don't take. But here we cut off a little bit of, we have to define the recursive formula a little bit more than just saying take all the different options, because we want to save certain recursive calls, right, with dynamic programming. So our two options are either don't take it, and then you earn fj minus 1 and b, right, because we didn't take the element. So we just take this. What does this symbolize? This returns the max amount of value we can steal with using just the j minus 1 first items, using a backpack that has size of b, right? This is our limitation on the weight. So this will return the max amount without taking j, which is what we want to calculate, right? If we don't take j and we're allowed to take up until j, it just equals this. Does this part make sense? Okay, now I'm going to continue to the next part. If we decide to steal it, then we earn vj, right? But then also you have to subtract the weight from b, right? So like we can still steal from the previous items, right? If we decide to steal j, we can still steal from the previous items. With 1 second, we can still steal from the j minus 1 previous items, but we only have b minus the weight of that item we took. So basically we have to call f with j minus 1, all the previous items, not including the jth item, with the weight of b minus wj, because we're subtracting the weight because we took the item. And then here you don't see it, but we're going to define it plus the value because we took the item.
We have.
Okay. Yes. Question.
So we don't include the value, the current value as part of the call because we return the value and like the actual value is the sum. Because like
Yeah, the function will return the maximum value that we can take. It'll just return it. We don't have to have a sum, an ongoing sum. This function call returns the max amount of value we can get from using the j-1 items and weight of at most b.
sure.
Okay? All right, so now let's define our recursive formula. Like we said before, it receives a j and a b and it returns something. So we already went over the base cases, right? So first we have the base cases. Base case is if j equals 0, we return 0 because we can't take anything. If wj is greater than b, then we have to just return the maximum of not taking wj because we can't take it, right? So the maximum, like the not taking it with b, with the same weight b. And then if we can take it, if wj is smaller or equal to b, so therefore we can take that same item, then we need to return the maximum between taking it and not taking it, right? That's what we said. So this is the not taking it. It's just calling it recursively on a smaller subgroup of items with the same weight. Or we take it and therefore we add the value, plus our recursive call, which is taking up until j, right? Not including j, and we subtract the weight because we took our item. So we return the max of these two. Now, is it understood why this returns if we call this on the amount of items n and our weight b? If we call it on that, do we understand why it returns really the max value?
Sorry. So I thought J was something different. You use J just to iterate over the items.
J is the items. If I have j equals 3, therefore I'm allowed to take the first item, the second item, or the third item.
Yeah, no, what I mean is like in this case, J is like an indicator of the index.
Yeah. It's basically not of the index. We still didn't get to like dynamic programming with indexes, but it's basically the place where we're allowed to take items up until that place.
Yeah, but like
You can only take the first G items.
so
yeah,
here,
only the first. Yeah,
here you're not taking the item, right?
here we're not taking that.
Yeah,
exactly.
but
we
use
still
J
can
anyway.
take exactly. We can still take if let's say j equals 3.
Okay.
We don't take the third item, right?
Yeah.
So we call it recursively on j-1 items, on the first j-1 items.
Sure.
Okay.
Yeah.
All right.
Wait, I've got a question.
Yes.
Oh, I can no longer see you. I can only see my name. Okay. Why don't we include b equals 0 in the definition of the function?
Like, I don't mean include. Oh, in the case of b equals 0, what I said earlier.
Yeah, in a case where b equals 0, we also.
It's true, but it'll be covered by this base case, right? It'll be covered by this base case because when j equals 0, it equals 0. If b equals 0, then no matter what j is, it'll just call itself on previous, like the previous j. So if j equals, let's say 5, right? And b is 0, so we'll always be in this case where wj is greater than b because b is 0. Therefore,
right, so we'll keep on going
we'll
until
keep on going back until we get to j equals 0, and it'll fill up that whole thing with zeros. Okay. Technically, you could do it manually, but this is just a little bit clean.
Okay.
All right. Runtime of this formula, as we know from our recursive formulas recitation, we call it in worst case we have 2 separate calls, and each one the input decreases by 1, right? Each time we call it, j decreases by 1. So we're going to analyze it according to j. So each time it decreases by 1, plus at each time we have O of 1. Why O of 1? Because at each call, it's based upon sorry, not based upon the taking the max between these two is basically O of 1. It's basically O of 1. Okay, So first, before we get to that, I want to just make sure, because this is really important, because we're going to get to another question, which is a little bit more complicated. But is this understood, this formula? If you solve this recursive formula with let's see, substitution method, you would get a equals 2 to the power of n. You can also think about it like such. Imagine it being a tree, right? Where each recursive, it splits it by 2. What formula? We saw this where? In the recitation of, yeah, we definitely solved this in the recitation, yeah. Where each time it just splits into 2. The height of the tree would be n, and therefore we have 2 to the power of n nodes. Okay? This time it splits. Okay, so now after we understood this formula, which basically each time we limit the amount of items we can take, but we also limit the weight. Okay, so first, so if we call it on a certain, like on n and the big B, our total batch, it'll keep on calling itself until we get to the base cases, and then it'll fill itself back up, which would take O to the power of n. Now, why is that runtime so bad? Because this was a naive, right? The naive is just calculate all the options.
Because
And
we need to do it from above to.
exactly, that we have basically you already skipped to here. So first, why is it so bad? Because we did save a certain amount of cases here. We saved a certain amount. We didn't calculate all of the different options. We always make sure that it's a valid solution, right? We always make sure that our new item it doesn't surpass B, right? So therefore, we never surpass B. So we only compute the valid options, which is already should save us time, but it doesn't, because in the bigger picture in asymptotic time, it doesn't save us anything. Okay, and now to your answer, why can we improve it? Because we have redundant computations. It could be that we get to the same computation from 2 different recursive calls. If we just save that, we will improve the runtime. Okay.
What's the different runtime? Be
Hmm?
over.
We'll get to O of n. Well, not O of n, it would be O of n times B. We'll get there. Okay, so before we get to the dynamic programming solution, this is one of the steps of the solution that you have. I'll upload it to the homework. Also, Lambda didn't let me upload the presentation, so you don't have it right now on the but I'll upload it after the lesson is over, and you have the order of operations that we have. So the next thing that we have to do after we define the recursive formula. After defining the recursive formula, after explaining what it is, now we have to explain, we have to prove why this is correct. Why this will return the correct answer. Okay? So let's do that now before we get to the dynamic programming. All right, so we're going to prove a lemma for every j between 0 and n, and every b between 0 and b. The value of f, j, and b is really the max value that our robber can steal with these items and a bag the size b. Okay? So we're basically proving the correctness of our recursive formula. Now, how are we going to prove that? We're going to prove 2 things. The first one is first we're going to prove that you even can steal this amount from with the bag of size b, that it's a valid solution. Because if it surpasses b, then
It's not valid.
it's not valid, and therefore it can't be optimal because it's not valid. So first you have to prove that our solution here returns a valid solution. And then once we do that, then we prove that you can't take a certain amount of items that are worth more than what we return with the same items and the same bag. Okay?
Yes.
So first is proving that our solution is valid, and then proving that our solution is optimal. And you'll see this, it appears a ton, where in order to prove your recursive recurrence, you basically prove that first it's valid, and then you prove optimal. Okay, it's a structure. It's a certain template that you'll use a ton in dynamic programming. Okay, you see the ton in the homework. We'll see the other question. Okay, so the first claim is that it's valid, right? Now we're not going to prove it here. It's actually I'm going to upload. It's in Hebrew, but there's someone typed up the whole tilgul, so the whole recitation. So I'll upload that to the Lambda. And also, if you don't want to, it's very simple. It's very intuitive. Basically, it's just by it's with induction on J, but it's very intuitive because we basically our recurrence formula, right? How the way that we defined it was basically that if W is greater than B, we don't take it. So we're never going to surpass B. That's the intuitive solution. The proof itself is with induction. We're going to do something very similar for the second part. Usually I don't like not proving things, but it's very, very simple. We're going to prove the exact same thing, exact same way. We're just going to prove the second claim. Okay, so we can't basically never prove that it's optimal. The FJB is optimal that you can't take with this J elements and a bag the size of B. You can't take any other group of elements that is its value is more than what our formula returns and the weight is less than B. So proof with induction on J, the number of items we're allowed to take, and also for every B between 0 and B. So our induction is on J. We're proving J for every single B. Okay? Is that understood? Okay. So our base case is for J because induction on J, so J equals 0. Basically our base case, right? Therefore, for every single B, our function returns 0. And because of this is the reality of the fact is that you can only make $0 because if you can't take any items, you can only make $0. So therefore our base case is in fact correct. When J equals 0, it's correct for any B. It doesn't matter what the B is, it's correct for any B. And now we're going to assume that the claim is true for every J smaller than J. And we're going to prove for J. Classic induction. So this is also something that to prove optimality of something, we do this a lot. Let's assume for the sake of contradiction that there exists something that's more optimal.
Yes.
Okay?
Yeah.
This shows up a lot. Also in greedy. It's exactly how you solve it. It's exactly how you prove it. So let's assume that there's some sort of better, more optimal solution. In other words, we have some sort of F star with J and B, which returns a more optimal solution. Therefore, it's strictly greater than our solution. Okay? So we assume for the sake of contradiction that there is one that is greater than our solution. Now, let I be the indexes of the elements that this function decided to choose. Okay? Now we're going to divide it up into two cases. If J, our last element, is within I, therefore he decided our better, more optimal function decided to take it, then we'll just look at the items that F star chose without J. Okay? Basically, this is the solution that we can get from a bag of B minus WJ, right? Because we took the J items, so the recursive formula we'll call on B minus WJ, right? For the rest of the items, we have B minus WJ, and its value is, one second, and its value of this minus VJ,
Yeah. With that.
exactly, is on the other side. VJ is basically the value of J, right? So this, basically our optimal solution without J has to be smaller or equal to our optimal solution, right? Our original function with the J minus 1 items and B minus WJ. Why is this correct? Why does this have to be smaller than this? Okay, it kind of gives you a hint, but it's on Hata Induktia, the assumption of our induction, right? Our induction assumption was that for any J smaller than our J, any J type smaller than our J, including J minus 1, it's optimal. So we know that this is optimal. Therefore, if we take our f star and take away the value of vj, take away the value of that last item, we know it's less than our optimal solution on a smaller v. Okay? And once we know that, we'll just sort it a little bit. We'll just move this to the other side. So our f star of j and b is smaller or equal to, we move vj to the other side, equals this, which is smaller or equal to f, j, and b. Why? Because this is basically the definition of what our function does, right? Our function can either take j or not take j. This is the exact case where it does take j, right? And because this is optimal, it's greater than this. And therefore, it's smaller or equal to our actual recurrence relation, which is a contradiction because we assume for the sake of contradiction that it's strictly greater. F star is strictly greater than f. And here we prove that f star is smaller or equal to our optimal solution. I see it confused up.
No, it's not confused. I don't like this proof because we bound j to be the size of the array or the amount of items we have. So if you say that j is in I, you're talking about a different j. You're talking about an arbitrary j.
The j here? We're talking about an arbitrary, yeah.
Yeah, but j is the size of the original set of items, no?
Yeah. It's not the original set of items, it's what we limited the original set of items to be. You can take the items up until the jth item. There could be more items, but we're not allowed to take them.
Like for it to be actually correct, the original j must be the original amount of items. Recursively, you take
Oh, you mean recursively, if you call it on the first, like if you call it on n, then n is the amount of items. N is the total amount of items.
Yeah.
J
So
is just a certain amount of items.
J is a subset, but for the
Exactly.
Algorithm to be correct,
Mhm.
The original input should be the size of the set.
Exactly. The first input should be just n and the big B.
Yeah.
Okay.
So j in this case, you're using it both for an arbitrary item and also the size of the remaining items. I don't see how it makes complete sense. Like
What do you mean that? But here we're using J as like some
j
sort of
is we have j items left to check.
not left to check. It's not J is not the amount of left to check. If we have a group of n items, I'm just going to explain this. If we have n items,
Yeah.
we call the first time we call it with n, right?
Yeah.
J equals n. But then we slowly recursively call it on j minus 1, j minus 1, and at a certain point, j, let's say, equals 4, right?
Yeah. And
So what does this mean? It means that we can take up until the 4th item. We can't take the 5th item, we can't take the 6th item.
yeah,
we can't take the n.
because what you're doing is going recursively from the end of the list to the start of the
Exactly,
list.
exactly. Okay, so
Yeah.
that's your question.
So here j is an arbitrary point.
It's just an arbitrary, yeah, it's an arbitrary point. We're proving with induction on j. How does that work? When j equals 0, we prove the base case. And then we prove it if 0 is true, then also if j is 1, our function is correct. If j equals 2, now it's correct because we proved it on 1. That's how induction works. So it'll prove it for any n, including our actual n. For any j, including our actual n.
Sure.
Okay. So also come to me afterwards if you want me to explain it
I
more.
understand. Right.
Okay. All right. So now we did our first case, right? We did our first case if j is within I. I have to do a second case if j is not in I. And those are the two cases. We're basically just going according to the formula that we defined earlier, right? It was between the max of either taking it or not taking it. So if we don't take it, we assume for the sake of contradiction there's some better f star optimal solution, then if j is not within I, we do the same idea, but just now it's a little bit simpler because we don't have to do with the case that it's taken. So I is, let's denote by I the valid solution that our f star does. Oh, sorry, denote I a valid solution with the items up until j minus 1 and a bag size of b, and therefore f star of j and b, because it didn't take j, we know that this is smaller or equal to our optimal solution by the induction hypothesis. We know that this is optimal. So therefore, and this one is smaller or equal to our f, j, and b, because this one takes the maximum between this and actually taking it. So therefore, it's smaller or equal to our f, j, and b, and therefore contradiction. It's a little bit simpler than the previous one. Now this template, before we get to that, this template is gonna repeat itself a lot, so it's very important you go over it. Thomas, afterwards, come to me and we'll explain everything. Because it's very important that we understand this, because it'll come up a ton. So now, how do we turn that into dynamic programming? Dynamic programming is saving recursive computations using memory. So we're going to define a table the size of n plus 1 by b plus 1 from the bottom up, such that for every cell j and b in the array, the array in the place of j and b equals to f of j and b. So we basically define our table, our matrix, according to our recurrence formula. That's why you need to do this step before you do this step. And since we proved this correctness, then this correctness will just be directly because of that one. So what does, let's say we take this cell. This cell is some sort of j and b. What is it based off of? How do I compute that cell? And that's in the solution, you have to include how you calculate a specific cell. So first off, we say what each cell is, right? Each cell is the maximum value we can take using j items, the first j items, and a bag size of b. But how do we compute this? According to the recurrence formula, we just use this. What is it based off if we take an arbitrary cell?
The cell above it.
Exactly, the cell above it. And
the way less.
exactly. And so the cell above it, because we're doing j minus 1 still, but b minus wj, so it'll be some cell here. Right, so it's based off of two different cells that are the row above it. So therefore, because we build it from the bottom to top, it all takes O of 1. Actually, here it's backwards. It's from top to bottom. We're going to fill the first j equals 0 row, and then j equals 1. We'll fill that whole row. Each cell is based off of this cell is above it. And the cells in the row above it. So therefore, if we have this whole row, then we can calculate this whole row, and so on and so forth. So we fill it row by row by row. And that's something you have to include in the solution, is you have to explain how you fill out the table. Okay? So the first row is all zeros, and then for every cell, we just use the previous row to calculate it. And then you also have to state where the answer is going to appear. It's going to appear in the cell of n and b. Okay? Now, is it clear? It's very important to note, you have to explain how each cell is calculated. First, what each cell is, then how each cell is calculated, and how you're going to fill up your table or array. How are you going to fill it up? By rows, by columns. And then your last thing you have to say is where the solution appears. I'll put the order of operations in the homework, and also you'll see it when I upload the presentation. Make sure to do all the steps in it. And the runtime is O of n times b, because each cell takes O of 1 to fill, and we have n times b, table size of n times b, so n times b cells. All right, now Shihzul is how do we now go back and get the items. Our cell, right? The answer is the max amount of weight, right? The max amount of value we can take. But now if we want to go backwards and solve for the which indexes, right? You might want to solve which indexes. So therefore, we're going to have to do that in a little bit of a different way. So if we want to know which indexes, which items were taken, we're going to have to go through our table, which is now fully solved from the end to the beginning. We're going to start from the cell with our max value, with our n cell. And we'll know if that item was taken by just looking at the cell above it. Right? If that value, that max value equals the cell above it, that means that item wasn't taken. If that item does not equal the cell above it, it means we did take an item and you have to go to that place in the cell, in the table, okay? And then we just continue like that up until we get to the top of the table, which takes us O of n, because each time we go one row. So I'll just show you on the table how that looks. So let's say we start from here. We compare this element, this value in this cell to this value. If they're the same, that means we didn't take the nth item because they're the same. So we'll go to this cell and we'll keep on going until it changes. Second it changes, we know we took a certain value, right? We took that out, that item. And second, we know we took that item, we can skip to the correct cell by subtracting the weight of that item. And we so on and so forth continue up our array, each time keeping track of which items were taken. So we go through all the items from this cell up, each time checking, comparing it to the cell above it, and then keeping track of the indices.
Yeah, but how do you fill it up?
What?
How do you fill it up? Do you?
Oh, we already filled it up. We're assuming we already filled it up.
Oh,
It's the same table. Yeah, it's the same table.
yeah, no, yeah, but how did we fill it up? That's the question.
So this is how we fill it up. We said earlier.
Okay.
Okay. So if it's full, then you can get the original solution. You can get which items you actually took. And it takes us O of n time. Okay, so now the size of the table is O of n times b. But if you don't need to actually get the indexes, if the question just requires you to get the maximum value, then you can just keep 2 rows every time. You can always keep the 2 rows because each cell is based upon the previous row. If you keep 1 row and calculate the next row, you only need to keep 2 rows. Each one is size of b. And you can just calculate that. You can't then get the original solution back because you don't have the whole table. But if you don't need the original solution, if you don't need the items themselves, just need the value, you can use O of b space, just 2 rows. And that'll be also in the homework, I'm pretty sure, in one of the questions. Yeah.
You know the optimization that takes also of B space, and then you can restore the answer.
There is something, yeah. I don't remember right now, but we can
I can tell you on the way.
yeah, okay. We just have to finish. All right. So I have 10 minutes to finish this problem. Let's see how far we get. I'm gonna go really quickly, so try and bear with me, okay? All right. So story time. There's an office, and in that office, they want to organize a party. Now we're given a certain hierarchy of the positions. Each node represents a person. Each person has a boss. Each person has employees under him that he is their boss. Now we want to invite people such that each the people we invite, there's no boss and no employee that are invited together. So we can't invite this person and this person. Now each one of these nodes is a number representing the size of the family. Okay? So for each worker V, we have the size of his family. So we don't want a boss and an employee to come to the party. So we can invite 4 or 3. All right? And now we want to maximize the total amount of people at the party. Okay? So that's our, this is our problem. We have a tree with n nodes such that for every node V, we have a number representing the size of this family. And the output, we want the sum of the largest subgroup of nodes within this tree, such that there's no boss, there's no father and son like in the tree that are invited to the party. And that the sum of all the families of the nodes we chose is optimal. All right, so I'm just gonna go through this quickly. So for this example, really the optimal solution is all of these nodes. Notice we can't take 4 and 3 because
And also it's no direct boss.
exactly no direct boss. Exactly. If I invite a certain person and his family, I can't invite his boss, his direct boss.
Yeah.
I can invite like
Higher up.
higher up. So this is called maximum independent set, which is we want the maximum of all these nodes, but it has to be independent. We can't invite 2 people that are connected. Okay. All right. So let's first do the naive solution. Right. We'll do this quickly. We just are going to try all the different possible options of taking people. And we have to check if each one's valid and if it's optimal, right? So there's 2 to the power of n options. We have n different people. Each one we can take him or not take him. Then we have to check for every one if it's valid, if it's a valid choice, and then take a maximum between the valid ones, right? So in total, it's at least 2 to the power of n. Like we said earlier, n times 2 to the power of n. So we're going to define now the recursive answer. So we're going to have, instead of 1 recursive solution, it's not enough. We're going to have 2 recursive formulas. One is if we take the node that we're on, and the other one is if we don't take the node that we're on. Okay? So let's observe every time a certain node, okay? So we're going to have a different recursive formula for when V does come to the party, if V is invited, and if V is not inviting. So we're going to have 2 recursive formulas. So we're going to define I of V to be the biggest party we can have while choosing V and while inviting him to the party. So we can't have any of his sub-employees, right? We can't have any of them. We can't invite any of them. And E of V is the maximum, the biggest party that we can have, such that we didn't invite V. So now we can invite the sub-employees, okay? And then the final answer will be the maximum between taking the root and not taking the root. Sorry, taking the root and not taking the root. So far, straightforward. Now we have to define each of those functions. So first, let's define I of V. This is if we take V. So if V is a leaf, we're gonna return f of V, the total size of his family. And if V isn't a root, isn't a leaf, then what do we do? What do we do? We take the value because we take him, and the sum of all of his children, all of his subworkers, without taking them. This is the maximum party that we can get from their subtree without taking them. Okay? So because we can't take them, because we took because we took V, we can't take any of his subchildren. Okay, now if we don't take V, if it's a leaf, the base case is 0, right? Because we didn't take him. So therefore we return 0. And else, if we didn't take V, now we have an option. We can either take the child or not take the child, right? So we have to return the sum of the max between taking the child and not taking the child. Okay? All right, are the recursive formulas understood?
Yeah.
Stay. All right. Okay. So we're going to start from the leaves and then fill up because the leaves are the base case. We're going to keep a copy of the tree. And for each node, we're going to keep a field of I and a field of E. I is the biggest party we can have while inviting that node, and E is the biggest party we can have without inviting that node. Remember, it's in that subtree. So if it's a leaf, it's in that subtree of the leaf, which is just the leaf itself. So you think that because we start on the leaves,
I think the first study was something.
it's time to go home. It's okay, I'm almost done though. Well then?
Here.
No, for this interruption.
But pause the recording.
My brain is frazzled.